Okay, so another thing I want to talk about, it's actually nothing theoretical, but more practical, especially when you go into 2 and 3 dimensions, is that the way we construct there is actually a easier way or more pragmatic way of constructing the matrix and right-hand side. Okay. The more practical way is, instead of deriving a huge matrix like that in one shot, which is actually easy in 1D, but when you go to 2D and 3D and the unstructured mesh, it's actually very messy to actually derive the formula for the entire matrix. A easier way is to realize that the matrix, which is an integral over the whole domain, can be split into a summation of the integral over element I. So basically xi minus 1 to xi. And this is actually general. I mean, this is I actually goes from 1 to n plus 1, because here there are n plus 1 elements, right? So this is more general than this particular case in 1D. If you have multiple dimensions, it's the same, right? So basically, you are splitting this integral into an integral in each element. The advantage is that this integral in each element is usually a lot easier to construct. Okay? So first of all, this is actually a very, very sparse matrix in most of the time. Why? Because there are usually only very few basis functions that are non-zero within a particular element. Right? In the one-dimensional case, can somebody tell me how many non-zero rows and how many non-zero columns does this matrix have for a particular I? Oh, I think I a little bit confused you. Let's use a different index k, right? So this is basically this index should be separate from the I and j, right? So this is another third index k. So for each k, how many non-zero rows and non-zero columns are there in the matrix? Three? Are you sure? Which 3? So let's just pick one of the elements. So let's say this is k. This is delta xk. What are the corresponding i's and j's over which this is going to be non-zero? Yes, actually only when I is either equal to k or k plus 1, and if j is equal to k and k plus 1. This is going to have a chance of being non-zero. Okay, because if, let's say, I is neither k or k plus 1, then no matter what j is, the integral is going to be 0, because the first term is going to be 0. In addition, if j is neither k nor k plus 1, then no matter what I is, the integral is also going to be 0, because this is 0, right? So basically, this matrix, this entire matrix for any I and j is going to be non-zero only for 4 entries. There is only 4 numbers in the entire matrix. No matter how many elements there are only 4 elements. There are only 4 entries in the matrix that are non-zero. It's actually 2 by 2 submatrix. That's non-zero. Yes?
So you're talking about higher order. So this is, you just need to observe the first derivative, which this type of basis makes sense, which is the line. But if you would need to observe the second derivative, which you couldn't also use basis functions, could you?
Okay, so the question is, if you have to switch to a different basis function, which you do have to if you have a different equation, right? If you have a different space over which you have to discretize, you may have to use a different set of basis function. And in that case, this is called the element matrix for a given k, right? For a given element, I can construct an entire matrix for all i's and j's. It's no longer as sparse as this one, right? For example, maybe you want to enrich the basis function with things like that. So if you pick another grid point right in the middle of each element, you may have a parabola like that, right? Which goes from 0 to 1 and back to 0 and 0 elsewhere. So that's a way to enrich the basis, right? So in this case, this element matrix is going to be 3 by 3. I mean, there is going to be 9 entries that are non-zero. Okay, but like either way, it's going to be a very sparse matrix, because if you zoom into one element, there are usually a small number of basis functions that are non-zero, and all the rest of the basis functions are completely zero within that single element. Okay, so that's actually a benefit of choosing a nodal basis function. All right, so in this case, we can basically look at what these element matrix are. So for example, the first element, k equal to 0, right? So then we are looking at wx. We are looking at the first element. There is actually in the first element, there is only one basis function that is non-zero, right? So it's actually a lot easier. And my A1 is just going to be a single entry. So it's going to be 1 over delta x0 and 0 in the rest of the domain. So when k is equal to 1, so let's change the color. K equal to 1, we're looking at over here. So in addition to this, we have another basis, right? So my k2 is equal to, okay, so the first basis function is going to be non-zero. So we still have a 1 over delta x0 over here. But then again, this one is going to be non-zero because this is going to be the integral over x1, x2 of dw1 dx, dw2 dx, right? So it's this one times the derivative of this times derivative of this. So it's actually this is actually x1, not x0, right? So because I'm integrating over the green. And this is minus 1 over x0, this is minus 1 over x0, and this is 1 over x1, right? So this is all x1. So, and when we go to k equal to 2, we are now looking at this element. So this is A0, this is A1, this is A2. A2 now, the first basis function is completely 0 in the red element. So we have 0, and the first row are first column are 0. And starting from here, we get non-zero. 1 over delta x2 minus 1 over delta x2 minus 1 over delta x2 and 1 over delta x2. The rest is going to be 0. So basically, we can see that each element matrix is going to be non-zero within a small square, and it's actually the linear superposition of the summation of all of these matrices makes the entire matrix, right? So for example, this element is going to be, this entry is going to be added to this entry to make this 1 over delta x0 plus 1 over delta x1, and then this entry is going to be added to this entry that makes 1 over delta x1 plus 1 over delta x2. While all the off diagonals, they only appear in one of the matrices, so they are just a single entry, right? Make sense? So in a lot of finite element problems, the first thing to look at is how do I construct the matrix, assuming if I have only one element. right? So in this case, if I only have one element and I don't have any particular Dirichlet boundary conditions to restrict the space, I have a 2x2 matrix like that. And then the process of constructing the big entire matrix A is called assembly. I just take these small matrices, put the entries, put the rows and columns at the right place in the big matrix. And the same thing happens to the right-hand side. Due to linearity of the right-hand side, that integral can also be split into integrals over each element and then add them up. So assembly of the matrix can also apply to the right-hand side. Right? So in fact, if you look at the right-hand side, it's basically this plus this, right? Each is the integral over one of these elements. All right. Okay, so this is basically the practical way of doing finite elements.